Namaskar. Welcome to Prakash on Basics. I'm Prakash Zo. Last time I talked about the various parts of a nuclear reactor. Before that, we discussed how most of the reactions and other things related to a nuclear reactor work. So all the pieces of the jigsaw puzzle are there. We just have to assemble them together. So today we'll look into how the nuclear reactors actually work. Worldwide, nuclear energy provides anywhere between 5 to 10% of power. Depends upon the country, of course. Its maximum production through nuclear energy is, I think, in France. Uh, to make these reactors more efficient and safer, the reactor designs have rapidly improved over the decades in which they started their development, and things have progressed from there. Uh, so, nuclear reactors have a highly unique design. Let's first look into the basic principle of how nuclear reactors work, and that's pretty simple. Uh, mm, uh, a nuclear reactor in a nuclear power plant is basically a steam generator. The nuclear energy generates heat. It is used to produce steam. The steam runs the turbines, which turn and produce electricity in the generator. So it's nuclear energy, heat energy, mechanical energy, electrical energy. That's the chain. Um, Actually, in most of the power production that we know of, only the first step is usually different. The rest of the stuff is the same. Um, in thermal power plants where coal is burnt, the same thing happens. Gas plants, it's the same. Petrol driven generators, it's again the same. Geothermal energy, when it is used, it's again the same. So the first step changes, the rest of the steps are practically the same. In hydroelectric plants, that is hydel as it is known, or wind or solar, there are slight changes in the beginning part. Later on, of course, mechanical to electrical is always the same. Um, and I have talked of some of them right in the beginning when I discussed generators. Um, but overall, the actual process, the setup of a nuclear reactor is not all that simple. And there are many different types of nuclear reactors and or nuclear power generators. Mm, I'll first mention the ones that are most common. These are typically three. The first is what is known as the BWR, boiling water reactor. The next type is pressurized water reactor, or PWR. And there is then the CANDU, CANDU, Canada Deuterium Uranium Pressurized Heavy Water Reactor. So BWR, PWR, and CANDU. These are the most common type of reactors that are there worldwide. Uh, there are other types of reactors, but we'll talk of them sometime later, not now. Uh, uh, Among these, obviously, the earliest and the simplest uh, of reactors is the boiling water reactor. So let's understand that type of a reactor first. Um, BWR, that is boiling water reactor, is also sometimes referred to as LWR, that is light water reactor. because it uses H2O. Uh, that is the common water that we know of. There are close to about 100 of them in the worldwide scenario that we see, and over time they have been developed into six different types, 1 to 6, type A and so forth. All this started off right in the beginning, that is 1950s. um, Around 70s, and later on you had what were known as the advanced boiling water reactors. Then came the simplified boiling water reactors. Then came the economic simplified boiling water reactors, and so forth. uh, Usually, these boiling water reactors generate power in the range of 600 to 1400 megawatts. That's the range of power that is generated by these. Um, Now, how do they work? So, let us look into its design and parts. Uh, for that, you need a diagram. uh, I can't use diagrams from the book, special books, or on YouTube, because there are all those copyright issues. So you will have to make do with my ability to draw and understand things as they are. I'll mention the major parts, explain their function, and then let's look into the assembly and working of how all this goes about. We have two or three major buildings, as I told you last time. The containment building, the power generation, and the control room. These are the three major areas. But then the parts are like what they have been marked out. Uh, you have the containment building. That's the first step. It is has a very thick wall outside, about a meter and a half of concrete, and inside it is a very large steel container, which is used typically 10 meters in height and about 3 meters in its diameter. Uh, C represents the core. Uh, it contains the fuel cells or the fuel assembly, the control rods, and the moderator flows through it if required. The coolant flows through it if required, as and how it is required. The control rods, which absorb the neutrons, come up from below in case of the boiling water reactors. F represents the fuel assembly. It can be removed and replaced as and how it is required. R represents the cadmium or the hafnium uh, control rods, and they are introduced from below with suitable mechanism. DM represents the demineralized water, that's pure H2O. It's not only the coolant but also the moderator. P represents the variety of pumps. I've marked only one of them, but there could be more than one in the whole system. And there's a pipe that goes out as marked by the arrow, and that's through which DS, that is the dry steam, goes out. T1 and T2 are the high pressure and low pressure turbines. They are connected to the generator, and the symbol that you see by its side is the one that represents alternating current, as we had talked of long back. Uh, J is the condenser. This condenser arrangement is to condense the whole system down to water from steam. K represents the reheater, and that sends the water back again to the system. CR obviously is the control room. So that's the structural pattern that is around. I'm going to keep the diagram as it is, because as I discuss things, we should be able to understand how the working also goes about. But then I'll also talk of some additional information during the process. Initially, the core is subcritical. So very few thermal neutrons interact. There's hardly any heat produced. Uh, that's because the cadmium rods are inside the core, and they are all absorbing all the neutrons that are there around in the system. The demineralized water is pumped into the steel container. Uh, as it enters, it actually moves from up downwards from the sides, and then from the lower part enters the core of the system. Naturally, this water is both the coolant as well as the moderator. That is, it cools or takes away the heat that is being produced, as well as it slows down the neutrons. Fast neutrons slow down to thermal level. That is, they become slow neutrons. Mm. As the rods are gradually pulled out, the criticality constant K starts increasing, and the reactor goes from subcritical to critical to supercritical. I've talked of this long back, but I feel I should talk of this once more. This constant K is x upon y. Uh, x and y are the two terms that I'll first explain as I go along. Uh, y represents how many thermal neutrons are available for a particular step of a reaction, a nuclear reaction. What the nuclear reaction is, we have already discussed long back. So let's make numbers pretty simple. Let's say 100 thermal neutrons cause the reaction. So Y, the number available, is 100. Now, naturally, as I had told you, every one of them releases 3 more fast neutrons. So there will be 300 fast neutrons that come out. The water acts as the moderator, and then their speed starts reducing. And the cadmium rods are already present there. So let's say they are in a position that absorb 90% of these neutrons. So 90% of 300, that is 270. So 270 get absorbed. So only 30 thermal neutrons are available for the next nuclear reaction. So this means that the value of X is 30. So K, the constant, is 30 upon 100. How many are available afterwards divided by how many caused the thermal reaction. That's 30 upon 100, which is 0.3. Very simple. Since the value is less than 1, this is subcritical. So the reaction naturally is going to gradually slow down and fizzle out. So the temperature, whatever is there, will remain very low or will drop. Now, gradually the rods are pulled out. As they get pulled out, they start absorbing less and less number of neutrons. So let's say the number drops from 270 to 200. If 200 get absorbed, only 100 will be left. and these have been moderated. So the value of x will become 100. The value of y, what we started off, was also 100. So x upon y will be 100 upon 100, which is 1. And so the reaction becomes capable of continuing on its own. And so it becomes a continuous chain reaction, and the reactor is said to become critical. Now, suppose I want to raise the temperature further. So what do? I pull out the rods a little more. As soon as the rods are pulled out a little more, they will absorb less number of neutrons. So naturally, let's say only 150 of them get absorbed. So 150 remain, and so 150 can cause further reaction. So the value of x is 150. I started with 100. So the value of k has now become 150 upon 100, that is 1.5. It has gone more than 1. So the reaction starts going faster and faster. Naturally, the temperature starts building up. This is going to result into more steam. That is going to result into more output in terms of electricity finally. So, logically, if the cadmium rods or hafnium rods are pulled out, the value of K starts increasing. It becomes supercritical. Temperature starts becoming more. Electricity generated becomes more. If the rods are pushed in, the neutrons get absorbed. So it becomes subcritical and the temperature begins to drop. Naturally, steam produced also drops and the output in terms of electricity will also drop. So this is the way in which the control mechanism works. You must realize one more thing. Within the reactor vessel itself, the water is under pretty high pressure. A little bit of technical words. That's it's at 70 times the atmospheric pressure. So for people from engineering and other areas would realize that this value turns out to be 70 bar, or or about 70 to 75 atmospheres. That's practically as good as 1000 psi. Psi is pounds per square inch. That's the other terminology is that is used. But if you're talking in terms of MKS pattern, then all these engineering people will remember, or people from physics will know that it's as good as 7 to 7.6 megapascals. Let's keep the numbers aside. The pressure inside is close to 70 times the atmospheric pressure. So when you put pressure on a liquid, its boiling point rises. So naturally the boiling point of water will go up, and this will rise up to around 285 degrees Celsius or around 550 degrees Fahrenheit. So naturally the temperature is pretty hot, and this water, that when it enters from below into the core, in spite of its temperature, the boiling point being high, it starts getting converted into steam very rapidly, and that too at an extremely high pressure. The steam that is produced rises through the core and moves up. Now once it comes on top, the mechanism has not been shown here in the diagram, but the steam is dried. Uh, uh, Please remember that the steam that we usually are used to seeing contains water vapor, that is condensed particles of water on very small bits of air or other dust particles and so forth, and that's why it appears to be white. But if you dry it, then it's a transparent gas. So this dry steam is a transparent gas. Why? Because If you keep it wet and it enters into those turbines, it might condense there, and the droplets might not really be very conducive to the way in which the turbines turn and so forth. So dry steam is the one that is used, and then it also tends to retain the amount of heat that it possesses. Uh, this steam, dry steam, is the one that is taken out of that steel chamber and then goes to the turbines. I had last time mentioned, but I'll just remind you. It's like a turbine is basically a blade, like a fan blade, but only you don't have four or five blades. You have hundreds of them, and the whole thing is as good as a flat surface. Most of us, when we um, take up a flight and peep out or look at aeroplanes, you see those turbines that are turning inside. That's a turbine. Uh, so the steam enters from one side, and as it pushes through, it turns the turbine. And so this mechanical motion is the one that drives the generator. But realize that as the steam passes through, there is a drop in pressure because some of the energy has been used up, but the energy hasn't dropped too much. So as a consequence, there is quite a bit of energy left in the steam that is available. So what is done is uh, it is made to pass through a second turbine, which is the low pressure turbine, and that also then turns around and the steam goes beyond it. So both the turbines move together and cause uh, a turning motion in the generator, which generates the necessary electricity. Uh, the steam that goes beyond the turbines, one more step is taken. This is suddenly condensed down. That means it is converted back into water. When that happens, there is a fall in pressure rapidly. So if you keep it as steam itself, the net amount of pressure difference available on both sides may not be that high. But if you condense it down, the pressure difference is substantially large, so that the turning effect, because of the vacuum that is created on the other side, would result into more turning or more amount of energy being released. And that is why a condenser system or a set of condensing towers are used. That is that J part I talked of. And that is the one that results into uh, more amount of steam utilization. Now, once this is done, it is the water is sent back. It has to actually go back into the um, steel container. But before that, what is done is it is preheated, and that preheating is done in that part K. The reason is obvious. It has to go up to 280. If you have already converted it to a hotter to about 100, 120, 140, 50, then naturally this the amount of extracted amount of heat from the second step, or rather the next step in the core, would be a little better. So this, and then obviously there is also a pump that will increase the amount of pressure back again to the required 70 times atmospheric pressure, and the whole system then sends this demineralized water back again into the core. If during the process there is some loss, then additional water has to be also pumped into the system, and that can be pumped between the stages of condensation and reheating of the system, and this cycle then continues. So the core heats the water, converts to steam, the steam drives the turbines, the steam is then condensed, it is reheated and sent back to the core, and the cycle continues, and constantly heat is extracted from the core, which causes mechanical movement, which runs the turbine. The movement of the rods, the pumps, everything has to be electronically controlled. And for that, you have a separate control tower or a control mechanism or a control room typically, from where the whole process is controlled by suitably trained people. The top of this building B can also be removed, unscrewed, and the steel casing can also be unscrewed. And when required, the rods can be replaced. As I told you, there could be as many as 70 to 100 fuel assembly units with corresponding multiples of rods that are available. The assemblies are typically replaced every 18 to 24 months. Um, and the rods, the absorbing rods may also have to be occasionally uh, removed and replaced, but that's a rare part. So all this mechanism is how this boiling water reactor works. So we now know the process of how the boiling water reactor works. There is one more aspect associated with this. Sorry, the break was because I had to remove that diagram and shift it out. Uh, so what's vital in this? There are what are called three C's that are vital in any nuclear reactor or a power plant of this sort. And these are uh, control the power, cool the fuel, and contain the radioactivity. So if these three C's are taken care of, naturally the reactor will tend to remain safe and would remain harmless. So you have a control system. The nuclear reaction has to be constantly monitored and then controlled accordingly. But the basic control is by raising or lowering the absorber rods, um, or by controlling the flow rate of the water that is being pumped inside. And the reaction speed obviously is controlled by uh, putting the rods inside, slow down system, pull them out, increase the temperature that is being developed, or pump in more water or slow down the water flow and the temperatures would tend to build up and so forth. That's just simple mechanical process. Uh, the regulation of water flow uh, can also be used to control the amount of heat and the power output of the system. So the coolant, obviously in this case, to cool the fuel, you have to ensure that constantly water is there inside. Otherwise, the reaction will go become uncontrollable, and accidents like Chernobyl that you have all heard of could take place. Uh, Here, obviously, this demineralized water. Uh, why demineralize? Otherwise, it would tend to, the deposits would tend to corrode the systems inside. So it acts not only as the coolant to take away the heat and as the moderator because it tends to slow down the neutrons. Realize that there is a term in heat known as specific heat, and for water, this specific heat is maximum, which is 1. That is why water is preferred than using other liquids. And then how do you contain the radioactivity? That I have already mentioned. The thick concrete walls that are around the containment building provide the necessary protection against harmful radiation to the surroundings and to the people who are working there and so forth. Obviously, when the rods are replaced, suitable care has to be taken, and you have to ensure that the whole system is shut down, the rods are removed and stored in a specific manner. That's how a boiling water reactor works. But when they started using these boiling water reactors, uh, This radioactivity issue caused another problem, and that is what led to the next types of reactors that were developed. But that's the next logical step. So we will be coming to that. I'll talk of that maybe next time. If you've liked whatever I have said, please look up at a variety of diagrams that you might see on YouTube or in books that deal with an outlay of how the reactor looks and how the pictures are and how the three buildings are spaced out and so forth. Um, if you've liked whatever I have said, share this information with your friends. Now that you are wiser and know how nuclear reactors work, I'm sure you will be able to explain that to many others who are around you. And for ourselves, we must have this knowledge as we proceed. There are more things in nuclear reactors because that's a very important area nowadays. So that PWR and can do because it's important in India, and these breeder reactors, all these are more advanced types of reactors. I should give you a brief idea of those. So we'll come to that next time. Till that time, namaskar.